I welcome you all to my 15th lecture on digital signal processing, that is UEC 502 for electronics and communication engineering students and electronics and computer engineering students. Today we will do design of digital filters. And for that, we first discuss nth order linear constant coefficient difference equation again, which is indicated as summation k running from 0 to capital N ak yn minus k is equal to summation k running from 0 to m bk xn minus k. Here yn is equal to output and xn is equal to input, and yn minus k is delayed output by k samples, and xn minus k is delayed input by k samples. It can be rearranged as yn is equal to 1 by a naught bracket summation k running from 0 to capital M bk xn minus k minus summation k running from 1 to n ak yn minus k, and I mark it as equation A. Now these both equations are conveying same meaning, but these are recursive in nature. Now we consider that when n is equal to 0, then in this equation, this term goes 0 or becomes 0, and yn is equal to 1 by a naught summation k running from 0 to capital M bk xn minus k, and this is non-recursive equation. Now I can redefine it as summation k running from 0 to M bk by a naught xn minus k. Now we will define Hn as the impulse response of an LTI system, which is equal to Bn by n naught when n is ranging from 0 to capital M, and this Hn is 0 otherwise. And when I will substitute, instead of Bk by a naught, I will substitute here Hk, then it will appear to be a linear convolution sum, or I can represent it as Hn convolved with Xn through linear convolution operator. So this is an output of LTA system, and this impulse response can be of a filter. So LTA system can be a filter. Here this impulse response is finite. Therefore the impulse response of the causal of the concerned LTA system, which can be a filter, is having finite duration, that is 0 to capital M. It is non-zero over only a finite discrete time interval. Because of this property, this LTA system is often called a finite impulse response FIR system. So this impulse response is finite because it is having non-zero values for this duration only. But if n is greater than equal to 1, then look at this equation. This term becomes non-zero. So now this will be recursive equation. Note that the causal LTA system usually has an impulse response of infinite duration. The LTA system corresponding to equation A, together with condition of initial rest, will have an impulse response of infinite duration. And the example is Hn is equal to 1 by 2 raised to power n un. Un is step function. So Hn is non-zero for the range 0 n ranging from 0 to infinity. So Hn is a causal impulse response. Such systems are commonly referred to as infinite impulse response or IIR systems, because n is ranging from 0 to infinity, for which Hn can be non-zero. In the design of frequency selective filters, the desired characteristics of filters are specified in the frequency domain in terms of the desired magnitude and phase response of filter. In the filter design process, we need to determine the coefficient of a causal FIR or IIR filter that closely approximates the desired frequency response specifications by setting of these BK and AK coefficients. The FIR filters are employed in filtering problems where there is a requirement for a linear phase characteristic within the passband of the filter. This is very important. If there is no requirement for a linear phase characteristic, either an IIR or an FIR filter may be employed. Now, IIR filters are also having some benefits. The IIR filters have lower side lobes in the stop band than an FIR filters having the same number of parameters. If some phase distortion is tolerable, then an IIR filter is preferable because its implementation involves fewer parameters that requires less memory and has lower computational complexity. So it is application dependent that you want to go for FIR or IIR. FIR filters are having some advantages over IIR filters, which are as they have linear phase characteristics. FIR filters are non-recursive, therefore its realization is stable. Its design methods are usually linear. FIR filters can be realized efficiently in hardware. The FIR filter startup transients have finite duration. The FIR filters have low sensitivity towards the finite worth length effects. So these are some exclusive benefits of FIR filter over IIR filter. And in most of the applications where we require linear phase, we go for FIR filters. Now, next question is, we know that all the ideal filters are physically unrealizable as discussed in the previous lectures, but why? So we will take one example. We can consider the case of causality in more detail by examining the impulse response Hn of an ideal low pass filter with frequency response characteristics H omega is equal to 1 for omega less than equal to omega c. Here omega c is cutoff and 0 when omega is lying between omega c to pi. This we have done in the previous lecture also. So by taking inverse DTFT, the impulse response of this filter is Hn equal to omega c by pi for n is equal to 0 and omega c by pi sine omega c n by omega c n for n not equal to 0. And we have done in the course of signal system, it is indicating a sinc function actually. Now I am plotting Hn with respect to n and I can view this diagram. It is clear from this diagram that Hn is non-causal and Hn is non-zero for n ranging from minus infinity to infinity, so it is clearly unrealizable. Now, the problem is we want to realize it. So for the possible remedy to make it realizable includes introduce a large delay n naught in Hn, that is h cap n is equal to Hn minus n naught, that is shifting of Hn by n naught samples, and arbitrarily setting h cap n is equal to 0 for n less than 0. Samples appearing on this side in the delayed version can be truncated. So I am shifting this by n naught units and truncating the samples appearing on this side, and it will give me this h cap n. The DTFT of h cap n is h cap e raised to j omega is equal to h cap omega. It is no longer an ideal frequency response, or no longer has an h cap omega no longer has an ideal frequency response characteristics. The Fourier series expansion of h cap omega results in Gibbs phenomena because we have truncated these samples. We have truncated h cap n arbitrarily. Then what are the necessary and sufficient conditions that a frequency response characteristic h omega must satisfy in order for the resulting filter to be causal? Now for that, we will consider h omega is equal to hr omega plus iota h I omega, that is real part of h omega and imaginary part of h omega. Then the answer to this question is given by Wiener theorem. And it follows that if Hn has finite energy and Hn is equal to 0 for n less than 0, then integral absolute value of Ln absolute value of h omega d omega must be less than infinite. And this, the detailed proof is given in this book by Wiener and Pyle, 1934. And interested student can refer to this book. If h magnitude h omega is square integrable, and if the integral is finite, then we can associate with magnitude h omega a phase response phi omega, so that the resulting filter with frequency response h omega is equal to magnitude h omega e raised to j phi omega is causal. So these are two conditions, that is magnitude h omega is square integrable and its integral should be finite. And then the resulting filter will be causal and can be represented as this. H omega is equal to magnitude h omega e raised to j phi omega. Now inference regarding Pyle-Wiener theorem, that is from this formula, the magnitude response magnitude h omega can be 0 at some frequencies, but it cannot be 0 over any finite band of frequencies. That is, at certain frequency pi by 2 it can be 0, pi by 4 it can be 0, but it cannot be 0 for a finite band, since integral then will be infinite and this will not be fulfilled, so it will not be causal. So for causality, this condition should be fulfilled. And in addition to the Pyle-Wiener theorem, the causality also implies a strong relationship between hr omega and hi omega, that is real part of h omega and imaginary part of h omega. If Hn is absolutely summable, that is, if it is summable, it is stable system, then frequency response h omega exists. For an absolutely summable, causal and real sequence Hn, there exists a relationship between hr omega and hi omega as, that is, imaginary part of h omega, that is hi omega is equal to minus 1 by 2 pi integral from minus pi to pi h r lambda cot omega minus lambda by 2 d lambda. This is called discrete Hilbert transform. And the detailed solution is given in the book by Rabiner and Gold, and the interested student can refer to that book, as this is an article of advanced digital signal processing. I'm not going to describe it here, but you need to understand or know this condition. The causality imposes following implications in the design of frequency selective filters. The frequency response h omega be 0. The frequency response h omega cannot be 0 except at a finite set of points in frequency. I repeat once more, the frequency response h omega cannot be 0 except at a finite set of points in frequency. The magnitude h omega cannot be constant in any finite range of frequencies, and the transition from passband to stopband cannot be infinitely sharp It is consequences of Gibbs phenomena which results from the truncation of Hn at to achieve causality. Look at this. Abruptly set h cap n is equal to 0 for n less than 0. These samples have been truncated. So the Gibbs phenomena comes into picture, which results from the truncation of Hn to achieve causality. So this is very important. The truncation from passband to stopband cannot be infinitely sharp. The real and imaginary parts of H omega are interdependent and related by the discrete Hilbert transform by this formula. Therefore, the magnitude H of H omega and the phase phi omega of H omega cannot be chosen arbitrarily. They are strongly related with each other. From this, they are strong, the magnitude and the phase cannot be chosen arbitrarily. Now here we limit our attention to the class of linear time invariant systems specified by the difference equation, which are causal and realizable. So once more, this equation yn is equal to minus summation k running from 1 to n ak yn minus k plus summation k running from 0 to m minus 1 bk xn minus k. The corresponding system response is obtained by using inverse DTFT. It follows that y omega, I am taking DTFT of yn, y omega by x omega is equal to h omega, and it is summation k running from 0 to m minus 1 bk e raised to minus j omega k divided by 1 plus summation k running from 1 to n ak e raised to minus j omega k. Now here I have considered range k running from 0 to m minus 1. Therefore, there are m values of bk, b0 to bm minus 1. The basic digital filter design problem is to approximate any of the ideal frequency response characteristics with a system that has above frequency response h omega, this, by properly selecting the coefficients ak and bk. So once more I repeat, this is h omega is indicating the frequency response of an LTH system. The basic digital filter design problem is to approximate any of the ideal frequency response characteristics with a system that has the above frequency response h omega by properly selecting the coefficients ak and bk. So I need to choose ak and bk, and the correspondingly or typical magnitude response of physical realizable filter is like this. Like this is for the low pass filter, that is magnitude h omega with respect to omega. Now here there are ripples in the passband. This is the passband 0 to omega p, and stop band starts from omega s, and this is transition band. Delta 1 is passband ripple as shown, delta 2 is stop band ripple as shown, omega is passband edge frequency as indicated, omega is stop band edge frequency as indicated. So this is very important diagram because it indicates the ripples in the passband as well as in the stop band, and it indicates the transition band also. So very important to learn. A few common characteristics of practical frequency-selective filters. That is number one, magnitude of h omega cannot be constant in the entire passband of the filter. A small amount of ripple in the passband is usually tolerable. Look at this. The value of ripple is denoted as delta 1. It is 1. It is 1 plus delta 1. It is 1 minus delta 1. And the magnitude of h omega varies between the limit 1 plus minus delta 1 in the pass band. So this is the passband ripple, and this is the range of variation. It is not necessary for the filter response h omega to be 0 in the stop band. A small amount of ripple in the stop band is also tolerable. The ripple in the stop band of the filter is denoted as delta 2. So this is delta 2. Peak amplitude is delta 2. If we use logarithmic scale for magnitude of h omega, then ripple in passband is 20 log 10 delta 1 dB, and that in stop band is 20 log 10 delta 2 dB. The width of transition band, that is transition region, of filter is defined as magnitude omega s minus omega p. Here I would like to mention that omega, small omega, is angular frequency in discrete domain. The width of passband is usually called the bandwidth of filter. In any filter design problem, following attributes need to be specified. Number one, maximum tolerable passband ripple, maximum tolerable stop band ripple. So this delta 1 is maximum tolerable passband ripple, delta 2 is maximum tolerable stop band ripple. Passband edge frequency omega p and stop band edge frequency omega s. So this need to be defined, and with it, from this I can calculate transition width or transition band or bandwidth. The degree to which h omega approximates the specifications depends on the criterion used in the selection of filter coefficient ak and bk, as well as on m and n. What is m and what is n? I will justify it. Here we have done that this is response of an LTI system, and by this LTI system I am going to approximate the desired frequency response characteristics of filter through the setting of BK and AK. So it is all dependent upon how we choose BK and AK. So it is the criteria by which, selection criteria by which we select BK and AK, and what is the value of N and capital M. It will decide what is H omega. So it is rightly written that degree of to which h omega approximates the specifications depends on the criterion used in the selection of filter coefficients ak and bk, as well as on m and n. Once more I repeat that this diagram is very important because it is giving all the information about the frequency response of the low pass filter, that is delta 1 passband ripple, delta 2 stop band ripple, omega p passband edge frequency, omega s stop band edge frequencies. And the ripple in passband is 20 log 10 delta 1 dB. So while doing numericals, we need to be careful about that how to calculate delta 1, delta 2, and make other design calculations based on this. So in the question, these attributes will be given to you and you will have to design the filter. These are some of the books related to the lecture. And that's all for today's lecture. Thanks for attending this session on DSP. See you in next lecture.